Well, good morning, physics students. It is Tuesday, May 19th, 2020. Hey, today we're going to keep it pretty short. I want to work one more circular motion problem through with you as a sample. I want to take a look at one slightly more involved just to try to guide you through, what's this thinking process? How do we put the pieces together? The individual steps are all easy. I mean, it's just basic math and algebra. The physics comes in that processing and see how do we make the connections, how do we relate our pieces. So I wanted to work through another sample with you. Please catch working a sample with you, okay? So you should be working with me. Excuse me. So here's our problem. We got a 13,500 Newton car traveling at 50.0 kilometers per hour. Rounds a curve of radius 200 meters. I put a decimal point there to signify 3 sig figs. A, what is the minimum coefficient of friction between the tires and the road to keep the car safely on the curve? B, what is the maximum safe speed for the car on a rainy day when the coefficient of friction is 0.0500. All right, so we got two problems. Let's just go through and identify what we know. So up here, 13,500 newtons. Well, that's the Newton is a measurement of force. What force? This is the weight of the car. So I'm going to say that's FW. And it's traveling at 50.0 kilometers per hour. Kilometers per hour is a unit of speed or velocity. I'll call it a velocity. Technically, velocity should have a direction, but we know that speed and velocity are the same labels. They're calculated the same way. Rounds a curve of radius 200 meters. Well, gee, it tells us that this is a radius. Okay? And then what are we looking for? Well, in this part, we're looking for the coefficient of friction. In the second part, it's going to give us a coefficient of friction, and we're looking for a velocity. Okay, so there's two different problems here, different information. So, all right, first one, we're looking for that coefficient of friction. So what I did on this page is I just listed our information. We had our weight, our velocity, our radius, and we're looking for mu. If I just draw a little picture, here's our road, and we've got our car driving. So there's our velocity, right? And if we didn't have friction between our tires and the road, this car would just go right off into what I guess I've learned to call it is the pickers, okay? And we don't want to drive into the pickers. So we got a velocity, the weight of the car is pushing against the road, the radius. So this curve is part of a circle. And so we know the radius is 200 meters. So we got R, we got V, we got FW. Okay? Looking for mu. Well, how do we relate friction in this? And so the reason this problem comes in this chapter with circular motion is there are lots of forces that can cause things to move in a circle. Now, anything that moves in a circle is called a centripetal force. In this case, what makes the car move in a circle? I've already said that. It's the friction between the tires and the road. If there were no friction, car just keeps going in a straight line. Newton's first law, an object keeps doing what it's already doing. In order to change the motion of an object, Newton's second law, we need a force. A force on a mass causes an acceleration. So in this case, the centripetal force is the friction. Well, all right, Now we've got a formula for centripetal force. Centripetal force is mv squared over r. And we've got a formula for friction. Let's see. If mu equals force of friction over the normal force, then friction is mu times the normal force. So if I just realize that friction is my centripetal force, and I have a way of calculating friction, and I have a way of calculating centripetal force, we'll set those equal to each other. Now let's take a look. I'm looking for mu. I need to know my mass. I can find my mass. I know that my weight is 13,500 newtons, and weight equals m times g. So I could just take 13,500 newtons divided by g, and I would get my mass. I think I see a trick to do, though. I'm going to show you this. My velocity, 50 kilometers per hour. Okay, you've been in class for a semester. You ought to look at that and say, hey, those labels don't match the rest of what I'm working with. I'm going to have to do a unit conversion on that. R was meters. That's okay. Over here, mu is what we're looking for. All right, what is the normal force? How much force of contact does this car have with the road? And it turns out that would be its weight. But if I use the equation that weight equals m times g, if I could plug in where this normal force is with a weight, but then the weight is really m times g, I could actually simplify this thing a little bit and just say, hey, I don't even have to worry about the mass or the weight of the car. I could cross off the mass because they're on both sides, and I could just use g. Now, if you have to, rewind that video a little bit, play that back again. I just thought that might be a simpler way rather than converting this to find the mass, and I can just do my algebra a little bit and the mass drops out. I'm going to extend my page a little bit here. I'm going to get mu by itself, so I'll divide by g. So over on this side, well, here, divide by g and divide by g. So mu equals v squared over g times r. All over g times r. All right, before I go any further, I'm going to take care of a unit conversion. We've got 50 kilometers per hour, and I know that 1 kilometer is 1,000 meters, and I know that 1 hour is 3,600 seconds. So I'm going to cancel off my kilometers, and I'm going to cancel off my hours, and I'm going to get a velocity in meters per second. That's going to mesh with our other quantities much, much, much better. Could I have put that right up in there? Yes, but it's going to get messy, because then I'm going to have to square that. I'm better off just doing this conversion first. 50.0 times 1,000 divided by 3,600 equals 13.9 meters per second. All right, now let's go up here, and we're going to take 13.9 meters per second, and again 13.9 meters per second, and we're going to divide by g, which is 9.80 meters per second squared, and we're going to divide by the radius of 200 meters. Let's look at labels. Meters, 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 meters. Second squared, second squared. All the labels are gone. Hey, that's good news because this is a coefficient of friction. It doesn't have any labels. It's a ratio. So let's go 13.9 times 13.9 divided by 9.8 divided by 200 equals 0.0986. There's my coefficient of friction. All right. We just had to make a few reasoning steps along the way. The math really is pretty simple. You got to remember things like units. And it saddens me, but some of you still are reluctant to write down units on your work. And I don't know how. It's kind of like whenever the units get tricky, you just say, oh, I'm going to just ignore them. And that's when they're most important to pay attention to. Because if I ignore my units on this, I'm going to get a wrong answer. Got to do it. All right. So, how about the second part? In the second part, we were told the coefficient of friction, and now we're going to say, all right, so it's wet out. We know that we got to slow down when it's wet out. What's our safe velocity when the friction is just this? So, let's use similar reasoning. The centripetal force is still the friction. The centripetal force is m v squared over r, and the friction is mu times Fn. And we know that Fn is the weight, which is mg, so we could really say that m v squared over r equals mu mg, not omg. So m crosses off. And I just got to multiply both sides by r. V squared equals mu rg. So V is the square root of mu rg. And we do our math. V equals the square root of mu, which is 0.0500, times r was 200 meters, times g, which is 9.80 meters per second squared. If I look at my labels, I'm going to have meter squared on top, second squared on the bottom. When I take that out of a radical, that's meters per second. Feeling pretty good about this. Square root of 0.05 times 200 times 9.80, close parentheses, enter, and this tells me 9.899, so I guess that'd be 9.90 meters per second. Now, the problem didn't specify labels, so I can leave it there, and by comparison, I could look back and say, on the original problem, we were traveling 13.9 meters per second. Now we're going 9.9 meters per second. So what is that, like 60, 70%? 60% of the speed? Not sure if I'm doing my mental math right. But, hey, let's go ahead and do one final step and convert that to kilometers per hour. So we just reverse things. 9.90 meters per second. And there's 1,000 meters in a kilometer. And there's 3,600 seconds in an hour. So seconds cross off, meters cross off. 9.9 divided by 1,000 times 3,600 equals 35.6 kilometers per hour. I can do a little easier mental math. Yeah, that's about 70% of what we were before. So, gee, we actually have to slow down when the roads get bad. There are some people out there that probably could use that lesson. I had really wanted to this year. I had thought about this and we just never got around to doing it. But I thought about trying to freeze some trays of ice and getting a car tire and trying to actually do some measurements of the coefficient of friction of that car tire on a slab of concrete, on a slab of blacktop, on a slab of ice, and just try to see what we could come up with for measurements. I guess that'll have to wait to some other time. All right. Work on your problem set. Let me know if you have any issues.